Hey everybody, hope everything is good. Um, I know it's Thursday, so some of you have been taking AP tests all week. I hope those are going okay. I know they're not fun, um, but hopefully you're hanging in there and slugging your way through those. So this is our second lecture of the week. We're going to keep going with Ecell and some cell potential stuff, and we're going to start doing some relationships between cell potential and KEQ and delta G and some stuff like that. All right, today we're doing a pretty good job in this unit. This is going to cover a chunk of stuff today. Make sure that you're working through this stuff. I know you're busy, but don't get behind. Okay, try not to get behind. I'm worried about making sure that we get through everything and that you have some time to study for this final unit test and that you have time for the final exam. So we just want to make sure that we're working right along, right? And I don't want you to get too far behind. All right, so let's go ahead and get started and get this lecture going. So today we're going to start with the relationship between cell potential, or E0 of our cell, and KEQ, which is our equilibrium constant. And it actually is an equation. So E0 of our cell is actually equal to RT over NF ln KEQ. All right, now this actually can get simplified down because we know some things. All right, if this is at standard state, okay, our gas constant doesn't change. We know our temperature is 298, and F is Faraday's constant. So we know these two numbers and we know F. Okay, so this actually can be reduced down. So we can reduce this to E0 of our cell equals 0.0591 all over N log KEQ. Okay. So N is the number of electrons transferred in the half reactions. And KEQ is our equilibrium constant. So we can calculate KEQs if we have cell voltages and vice versa. All right, so remember, so if we have big KEQs, right, it favors our product side. All right, if we have small KEQs, it's going to favor our reactant side, and that's going to have an effect on our voltage. Right, so let's go ahead and try one of these. Determine the equilibrium constant for the displacement of copper 2 by zinc metal at standard conditions. Right, so we need to write this equation first. Okay, so we have Cu plus 2, and that would be an aqueous, with zinc solid going to Zn plus 2, aqueous, plus Cu solid. Right, now, this is the equation that we've been working with on and off for most of these notes. We've written our half reactions multiple times, all right, and if you look back, we know that 2 electrons will be transferred. Okay, so if we write the half reactions, because that's where we would get this, all right, we would figure out that 2 electrons are transferred. Right, now, we're going to end up using this relationship up here that we just talked about. So to calculate our K, we need our cell potential. So E0 of our cell is equal to E of our cathode minus the E of our anode. And we've actually already done this calculation also. So it's a positive 0.34 volts minus a negative 0.76 volts, which gave us a positive 1.10 volts. All right, so now we have enough to actually calculate KEQ. All right, so E0 of our cell is equal to 0.0591 all over N log KEQ. Well, we know this. It's a positive 1.10 volts equals 0.0591. N is the number of electrons transferred. Log KEQ. And when we do that math, our KEQ is equal to 1.7 times 10 to the 37th, which, okay, so what is this telling me? This is a huge K, all right? Extremely large K, which tells us it wants to go to basically completion. It wants all products. Okay, so in this equation up here, this is the KEQ is telling us that it's gonna produce all these products, okay? So this reaction is gonna keep going and producing voltage until it goes to completion, or until it reaches equilibrium. And at equilibrium, okay, once we reach equilibrium, we'll have all products. No more voltage will be produced. Okay. So we're going to talk a lot about these relationships between Ks and cell voltages, and we're going to get into delta Gs also. So let's talk about that relationship between free energy, which is our delta G, and KEQ. And our cell potential, all three of them. So we know that delta G0 naught, okay, so delta G at standard state is equal to negative RT ln KEQ. Okay, so we know that a spontaneous reaction has a negative delta G. So if we look at this, the more negative delta G, the larger the equilibrium constant. All right, so if we have that big equilibrium constant, that tells us we have a greater tendency to go to products. And we actually just talked about this in our last example. Now, we already have a relationship between KEQ and cell voltage. we have a relationship between delta G and KEQ, which means we have a relationship between delta G and our cell potential. All right, so we can manipulate equations, and I'm not going to go through those manipulations. If we were in school, I probably would. All right, but I'm not going to go through the manipulations. All right, so I'm just going to give you the relationship. So our relationship is delta G0 equals negative N Faraday's constant E of our cell. So that's our delta G. This is Faraday's constant. This is moles of electrons. This is our constant. All right, there's our cell potential. Now, what is this telling us? Okay, if we just look at this equation, the more, okay, if we remember, we said a reaction is spontaneous if E0 is positive. Okay. So if E0 is positive, all right, the more positive it is, that makes delta G more and more and more negative. So the more positive the cell, we know that this is a spontaneous process. It's a spontaneous reaction. All right. So the more positive it is, this is also telling us that it's a spontaneous reaction. Okay. So the bigger positive this is, the more negative this becomes. Now, what if this is negative? Well, if E0 of the cell is negative, we said that's non-spontaneous. That turns delta G into a positive number, which agrees and again says that it's a non-spontaneous process. All right, so let's go ahead and do some problems with this. So let's determine the standard free energy for the following. All right, now remember, we're at standard conditions for all of these. Okay, so we got 1 molar solutions, 1 atmosphere, 298 K. So we're at standard conditions. So let's go ahead and deal with the single replacement of copper 2 by zinc, which is the one that we've been dealing with. Okay, so we have Cu plus 2 plus zinc. This is aqueous. This is solid. Going to Zn plus 2 aqueous. Okay, plus Cu solid. Right. Now, we've already calculated this E0. This is telling us that it's spontaneous in itself, all right? But we can actually calculate the delta G, okay, using this cell voltage. So we know that delta G naught is equal to negative N F E0 of our cell. Well, N is 2 because that's the total number of moles of electrons. So if we do our half reactions again, we can figure out that 2 moles of electrons are transferred. Faraday's constant is 96485. We don't and our cell voltage is positive 1.10 volts. Okay, when we do that math, we end up with a negative 212,267 joules, which means it's negative 212 kilojoules. And I think we've actually already calculated that before in different ways. Okay, so remember, there's lots of ways to calculate delta G. Right? Again, this negative sign is telling us that it's spontaneous. Okay, you need to remember there's lots of ways to calculate delta G now. All right, lots of ways. Okay, so I'm just giving you another weapon in your arsenal, basically, to calculate your free energy. Let's try a second one of these. The reduction of tin 4 to tin 2 by the oxidation of Fe2 to Fe3. So tin 4 is turning into tin 2, iron 2 is turning to iron 3. So let's go ahead and write this equation. Sn plus 4, and these would all be aqueuses, plus Fe plus 2, aqueous, going to Fe, oops, that's an F, plus 3, aqueous, plus Sn plus 2, aqueous. Now, we are going to need cell voltage, and we need electrons, so we're going to have to write half reactions, and we're going to have to figure out E0 of our cell. All right, so Sn plus 4 is turning into Sn plus 2, and Fe plus 2 is turning into Fe plus 3. All right, so this one is gaining 2 electrons. This one is losing 1 electron. So we would have to multiply this one through by 2. So we ended up 2Fe plus 2 going to 2Fe plus 3 plus 2 electrons. All right, so our moles of electrons are going to be 2. Okay, so we need that information. All right, now we need the E0 of this cell. Well, to go from Sn plus 4 to Sn plus 2 is positive 0.15, right? So let's write that down. So let's see, Sn plus 4 to Sn plus 2 was 0.15 volts, and that's positive. And then the other one, we're going from Fe plus 2 to Fe plus 3. And that's a positive 0.77 volts. So when we calculate this, E0 over cathode minus E0 over anode. So we get 0.15 volts minus positive 0.77 volts. And that equals a negative 0.62 volts. What's that negative sign telling me? Well, okay, remember, negative sign tells me that it's non-spontaneous, that reaction's not going to happen. All right, so let's go ahead and put it into our equation. negative 2 moles times our 96,485 times a negative 0.62 volts. That gives us a positive 119,641.4 joules, which is a positive 120 kilojoules, which is telling us that this is a non-spontaneous process. Okay, this reaction is not going to happen spontaneously. Okay, for us to make, we would have to make this reaction happen. Okay, we would have to have an external power source to force this to happen. All right. We should probably try a harder one. Determine our delta standard free energy for the reduction of dichromate ions to chromium 3 ions by Mn plus 2 forming MnO2. All right. Dichromate ions. So we're going to start with our dichromate ion, Cr2O7 minus 2, Mn plus 2, going to MnO2 plus Cr plus 3. Well, we need two things. We're going to need cell voltage, and we're going to need the number of electrons transferred here. All right, now this is a more complicated balancing. We need those half reactions. So, all right, here we go. So we got Cr2O7 minus 2 going to 2, going to Cr plus 3, and we have Mn plus 2 going to MnO2. So here we go. All right, the first thing we need to do is we need to balance our masses, everything except our oxygens and hydrogen. So we got 2 chromiums on this side, so I need 2 chromiums on this side. All right, so then my MNs are good. Okay, so the next thing we have to do is our oxygens. So we're going to need to add, for every oxygen we add water molecules. So we're going to add 7 H2O over here. And down here we need to add 2 H2Os over here. Okay, so now that my oxygens are set, now we have to have hydrogens. So we're going to have to add 14 H pluses to this side. And then for this one, we're going to have to add 4 H pluses to this side. Right, now we have to look at electrons and our overall charge. So on this side, we have, let's see, on this side we have plus 6, and over here we have, let's see, this is minus 2, so that's plus, this is plus 14, plus 12. We said this was plus 6. All right, so this is plus 12 going to plus 6. So we're going to add 6 electrons on this side. Okay, let's look at our charges here. So that's 0. So this side is a plus 4, and this side is a plus 2. All right, so that means, that right? Plus 4 plus 2. So that means we're adding 2 electrons on this side. All right, so now we would have to multiply through this whole thing by 3. So we would end up with 6H2O plus 3Mn plus 2 going to 3MnO2 plus 12H plus 6 electrons. So we get through all of that. Okay, and we could write our net ionic equations, but what do we really need from this? The reason we're doing this is we need to know how many electrons are transferred, and it's going to be 6. Now, so that's the first part. Our E0 of our cell is equal to the E0 of our cathode minus our E0 of our anode. And we now know our anode and cathodes, and we can go look these up on the table. Right? So if we look them up, we end up with 1.33 volts minus positive 1.23 volts, which gives us a cell voltage of a positive 1.0 volts. Okay, so we get that positive value, which is indicating that this is spontaneous. Right? So now we can actually calculate delta G. Oop, that's an F. That's an F. So we have negative 6 times Faraday's constant times 0.10 volts. And when we do that math and convert to kilojoules, we end up with a negative 57.9 kilojoules as our delta G. And again, this is telling us that it's spontaneous. Okay. Now, let's just think about this for just a second. This is all under standard conditions. That means all of these solutions are 1 molar. Okay, all of these solutions are 1 molar. Well, what happens if the concentration of Mn2 is equal to something less than 1 molar? I don't know, 0.078 molar. What's going to happen to this cell voltage? Okay, so we know that we're moving in this direction. Okay. So if these are both 1 molar, these are going to keep reacting until eventually we reach equilibrium. All right. So this amount of this is going down. Okay. So what's going to happen? Okay, what's going to happen as this reaction happens? Well, the amount of this is going to decrease. Our concentration of Mn plus 2 is going to go down and down and down, and it's going to keep going down until it reaches its equilibrium. Well, if we look at this one, we're already below that 1.0. Okay, so our Mn plus 2 concentration is decreasing. Okay. And we're getting more and more product. Okay, so we're moving this equilibrium over to the right side. So if we have less Mn plus 2 to start, all right, okay, our voltage is going to drop. Let me see if I can say this again. So this number right here, this voltage that we calculated for this cell, is when this is 1 molar, this is 1 molar, right? When everything is 1 molar. Now, as this reaction happens, we're getting closer and closer to equilibrium. All right, which means we're shifting this way. So our products are increasing, these are decreasing. All right. What's that do to my cell voltage? Well, over time, that cell voltage is going to go down as this reaction happens until eventually we reach equilibrium and it's going to produce no voltage. So if this is starting less than 1, okay, our voltage is going to be less than 0.10 volts. So let's write this. As the reaction occurs, the concentration of our reactants is going to decrease and our voltage will decrease. At equilibrium, our voltage is equal to 0. Which takes us right into our next topic. All right, so this voltage calculation is at standard conditions. But as soon as we start using this battery, as soon as we put these together, these start reacting, and we are not at 1 molar anymore. Okay, so we're not at standard conditions, which means we're not going to be producing 0.10 volts. So this is nice to know how much energy can be produced to start with, but generally we're not at standard state, which changes the game a little bit. So let's write some things. So we now know that a cell will try and reach equilibrium. At equilibrium, we now know that E0 of our cell is equal to 0. So as a reaction moves toward equilibrium, its voltage decreases. So we start at the maximum and it slowly decreases down to 0. Now, let's talk about that for just 1 second. Do we see this with our batteries? Okay, and the answer is absolutely. Okay, so I don't know how many of you had a Wii, a Nintendo Wii, all right, with the thing that you held in your hand and you played Wii tennis and that kind of stuff. All right, so if you took, it ran on batteries. Right, so we put a brand new battery in there and we play our Wii tennis for like 5 hours. All right. And as we're doing it, the voltage of those batteries is decreasing because we're getting closer and closer to equilibrium. And eventually that battery or our Wii remote doesn't work anymore. Okay. Does that mean our batteries are completely dead? Well, if you take those, I think they were AA batteries, if you take that battery and put it in just like a clock, okay, it will run a clock. The difference between the two things, what happens is that battery is still producing voltage. It's not producing enough voltage to run a Wii remote, but it does produce enough voltage to run a clock. All right, so what happens over time in that Wii remote, all right, the maximum voltage starts, but as we use it, it goes down, down, and down, and down, and eventually the battery reaches a point where it's not producing enough voltage to run the Wii remote. But it is still not at equilibrium, so it will run like a clock or something that doesn't take much voltage. All right, so we can actually see this in our real batteries. We also know that if our cell potential is positive, it is thermodynamically favored and the equilibrium lies on the product side of the arrow or the equation. Right? So we know that our equilibrium lies over on this product side. Well, if it's on the product side, that means we're going to have a large KEQ. And we've actually already talked about that too. Now, we can use Le Chatelier to determine what will happen to cell voltage if we change concentration. All right. So let's try this. Let's see what we come up with. So let's say we have 2Ag plus CD solid, this is aqueous, going to CD plus 2 aqueous plus Ag solid. So let's just quick do our, I'm going to tell you that when the concentration of Ag plus and the concentration of CD plus 2, when those concentrations are 1 molar or standard conditions, the E0 of this cell is equal to 1.20 volts. Right. Now, it's a positive number, so that's telling us that we're producing, okay, it's spontaneous and we're going to products. All right, so it wants to go this way. It wants to go right, which is telling us that we're going to have a large KEQ. Okay. Which means we want lots of the concentration of CD plus 2, and we'll have little concentration of Ag plus at equilibrium. Well, what happens to this reaction then what happens to the voltage if the concentration of Ag plus is 0.1 molar? Well, remember, CD, we want lots of CD and little Ag. Okay, so at equilibrium, this is at equilibrium. Let's write that. Okay, at equilibrium, we want lots of CD and lots of Ag. And remember, at equilibrium, our voltage is 0. So the closer we get to these conditions, the less voltage we're going to produce. Okay, so now we've decreased the amount of Ag plus. Okay, so the concentration of CD plus 2, or plus 2, is greater than the concentration of Ag plus, which means we're closer to equilibrium. So if we're closer to equilibrium by looking at these concentrations, that means our voltage will have less voltage. So we now know that we will produce less voltage than 1.20 volts. Well, what if we look at the concentration of Ag being 2.0 molar? Well, if we compare the concentration of CD and Ag, okay, so we're not changing the CD concentration, that's 1 molar. Okay, the concentration now of Ag plus is greater than the concentration of CD plus 2. So we're going to have a greater voltage. Okay, we're going to have a greater voltage. So just by comparing concentrations, we can actually predict what's going to happen to cell voltage. Well, that's all well and good. Okay, that's all well and good. But in reality, we're going to want to actually calculate voltages. Okay, we're going to want to calculate voltages. Which actually brings us to what's called the Nernst equation. And the Nernst equation lets us calculate cell voltage at a non-standard state. Okay. So our concentrations are no longer going to be 1 molar. Now the Nernst equation is this. The E of our cell, okay, no naught, okay, because we're not at standard conditions, equals E0 of our cell minus 0.0591 all over n log Q. Okay, so this is a combination of a bunch of equations, all right, and you can see the different equations in there. And again, if we were in school, I would probably take you through the calculation of, or the derivation of this formula, all right, but I'm not going to. All right, we're just going to use this equation, but you can definitely see some of the parts of the equation. We've used this, all right, instead of log KEQ, we're using Q, which is our reaction quotient. Okay, so we've used, okay, you can see the parts, right? But this is the Nernst equation, and it will actually give us our cell voltage at non-standard state conditions. So let's try one. Calculate the voltage of the following cell with the following concentrations. So we're going to have 2Al solid plus 3Mn plus 3 aqueous going to 2Al plus 3 aqueous plus 3Mn solid. And our concentrations are a concentration of Mn plus is this Mn plus 2? This is Mn plus 2 is equal to 0.50 molar. And the concentration of Al plus 3 is equal to 1.50 molar. All right. Well, eventually we're going to need, eventually we need E0 of our cell, we need the number of electrons, and we're going to need Q. All right, so let's go ahead and calculate the E0 of our cell. All right, so we need 3 things. We need E0 of our cell, which is going to equal the E0 of our cathode minus the E0 of our anode. And we could write out the half reactions, figure out which is our anode and our cathode. So Mn plus 2 to Mn and Al plus 3 to Al. We'd look those up, figure out which one's more positive, All right, all those different things. Okay, so we look it up and we end up with negative 1.19 volts minus negative 1.66 volts. And that gives us a 0 of positive 0.47 volts, right, which is telling us that that's spontaneous. Next thing we need is we need our KEQ. Actually, we need our Q, our reaction quotient, okay, which is equal to the concentration of Al plus 3 squared all over the concentration of Mn plus 2 cubed. Okay, remember, solids don't go into them because they don't have a concentration. So we end up with 1.50 squared all over 0.50 cubed, which gives me a Q of 18. All right. Now I need, the last thing I finally need for this equation is I need N, the number of electrons that are transferred here. All right, so I really do need the half reactions, and I probably should have just done that first. All right, so turns out that I have 2Al0 going to 2Al plus 3 plus 6 electrons, and 3Mn plus 2 plus 6 electrons going to 3Mn0. All right, so I'm transferring 6 electrons, so our N is equal to 6. Now that I have those three things, now I can go substitute into this big equation, and I can actually get the cell voltage, okay, of what this actually is. Now at standard state, it produces 0.47 volts. Okay, we aren't at standard state though. Okay, we have more aluminum and less manganese. Okay, so here we go. So the E of our cell is equal to E0 of the cell minus 0.0591 all over N log Q. Well, we know what this is. We calculated it here. Positive 0.47 minus 0.0591 all over 6 log of 18. And when we do all that math, we get a positive 0.46 volts. So our voltage has gone down. Now, does that make sense that it's gone down? Okay, well, remember, okay, this is spontaneous, so we're going over here. At equilibrium, the Al plus 3 is greater than the Mn plus 2. Right, that's when our cell voltage is going down. So if we compare this, Al is greater than Mn plus 2 already in these conditions, so our voltage should have dropped. It's closer to equilibrium. Now, it hasn't dropped by much, but it has dropped. Right, so now we can calculate the cell voltage of any cell at any point now, okay, all the way up to equilibrium. All right, so you're going to need to practice some of this stuff, and you're going to be working on a lab, all right, doing some different things, all right, and you're going to be working with all this stuff. All right, so I don't see you again until next Monday. Have a good weekend, and we will talk to you soon.